Assalamu alaikum. Welcome to my YouTube channel. And today's topic about the solution method for PDEs. Analytic solution are possible, and for simple and special idealized cases only. To make use of the nature of the equations, different methods are used to solve different classes of PDEs. These are the solution methods for partial differential equations in higher mathematics. How to solve PDEs? And PDEs are solved together with appropriate boundary conditions and or initial conditions. Not that boundary conditions and initial conditions. And boundary value problem, Pritchett BC specify u of x comma y on boundaries say at x is equal to 0 comma x is equal to L comma x y is equal to Lx comma y is equal to 0 and y is equal to Ly in a rectangular box. Non-Newman BC specify normal gradient of u of x comma y on boundaries. Okay, Newman problem boundaries branch, and Newman means derivative involved. And principal boundary can be arbitrary shaped but difficult to implement in computer codes. Here's boundary values and boundary curves. Along the boundary curves, region governed by a different equation. These regions are governed by a different equation. These dots means governed by a different equations. Okay, then here is one-dimensional heat equation. This is a one-dimensional heat equation. Partially derivative u with respect to t multiple x comma t function is equal to beta partial square u or partial x square x comma t comma 0 less than x less than a and limiting point comma t greater than 0 comma u of 0 comma t is equal to u of L comma t is equal to 0 comma t greater than 0 u of x comma 0 is equal to f of x comma 0 less than x less than a. Then the method of separation of variables, introducing solution of the form u of x comma t is equal to x large capital X of x capital T of t. Substituting into the initial value problem, we obtain these are the initial value problem, and here the substitute x of x t dash of t first derivative of t is equal to beta x second derivative of x t of t 0 less than x less than L comma t greater than 0. This leads to the equation, to the following equations. Here is the equation constant, thus we have first derivative of t minus beta kt of t is equal to 0 and a second derivative of x minus kx is equal to 0. Boundary conditions imply that we are looking for a non-trivial solution x of x satisfying. We shall consider three cases: k is equal to 0 and comma k greater than 0 and k less than 0. X double dash of x minus kx of x is equal to 0. X of 0 is equal to x of L is equal to 0. Case 1, k is equal to 0. In this case we have x of x is equal to 0. Trivial solutions. Case 2, k greater than 0, let k lambda square, then the d differential equation gives x double derivative minus lambda square x is equal to 0. The fundamental solution set is here. A general solution is given by x of x is equal to c1 e power lambda x plus c2 e power negative lambda x. X of 0 is equal to 0. This implies that c1 plus c2 is equal to 0 and x of L is equal to 0. This implies that c1 e power lambda L plus c2 e power negative lambda L is equal to 0. Hence c1 e power 2 lambda L minus 1 is equal to 0. This implies that c1 is equal to 0 and so is c2 is equal to 0. Again we have a trivial solution x of x is equal to 0. Finally, case 3, when k less than 0, we again let k is equal to negative lambda square comma lambda greater than 0. The differential equations become x double derivative of x double dash of x plus lambda square x of x is equal to 0. The auxiliary equation is r square plus lambda square is equal to 0 as the auxiliary equation, or r is equal to plus minus 1 lambda I. The general solution x of x is equal to c1 is e power iota lambda x plus c2 is power negative iota lambda x, or we prefer write x of x is equal to c1 cos lambda x plus c2 sin lambda x. Now the boundary conditions x of 0 is equal to x of L is equal to 0 imply c1 is equal to 0 and c2 sin lambda L is equal to 0. For this to happen, we need lambda L is equal to n pi comma aya. Lambda is equal to n pi divides L, or k is equal to negative bracket start n pi our layer L bracket our whole square. We set xn of x is equal to n sin n pi over L x n is equal to 1 2 3 up to so on. Finally, for t dash of t minus beta k t of t is equal to 0, k is equal to negative lambda square, we write it as t dash plus beta lambda square t is equal to 0, or t dash is equal to negative beta lambda square t. We see the solutions are t n of t is equal to b n e power negative beta n pi over L whole square, t n is equal to 1 here, and here this n is equal to 1 2 3 be any value. This is the function un of x comma t. This is the function is equal to xn of x t n of t. Satisfy the differential equation and the boundary conditions. To satisfy the initial condition, we try u of x comma t is equal to summation un x comma t over all n, more precisely u of x comma t is equal to summation 1 from 1 to infinity c n e power negative beta n pi over L whole square t sin n pi over L x. We must have u of x comma 0 is equal to summation. This is also compact form. We use compact form to represent this series, and infinity c n sin n pi over L x is equal to f of x. This leads to the question of when it is possible to represent f of x by the solution called Fourier sine series. This is the Fourier sine series, and we use the compact form to represent this series in this form. This is the compact form. And example, solve the following heat flow problems. Partial u or partial t is equal to 7, partial u or partial x square. These are our heat flow problems. Okay, and wave equation. Now we have a wave equation on heat flow problem. In the heat flow problem, in the study of vibrating strings such as piano wire or guitar string, partial square u or partial t square is equal to alpha square partial u partial square u or partial x square 0 less than x less than L, t greater than 0, and here are all using heat flow problems. And the vibrating string such as piano wire itself. And example, f of x is equal to 6 sin 2x plus 9 sin 7x minus sin 10x, and g of x is equal to 11 sin 9x minus 14 sin 15x. The solution is the form. Here is the form. And classes of partial differential equation. Partial differential equation can be categorized as boundary value problems, or initial value problems, or initial boundary value problems. The boundary value problems are those problems that the complete solution of the partial differential equation is possible with a specific boundary condition. The initial value problems are those partial differential equation PDE for which the complete solution of the equation is possible only with specific information at one instant. Solution of partial differential equation by separation of variables. This is the other solution. The essence of this method is to separate the independent variables such as x, y, z and t involved in the function in the equation. This can be done by assuming the original function or instant f of x comma y comma t's function to be, here is a function is equal to f1 of x, f2 of x, f3 of x, in which f1 of x function of x only, f2 of x function of y only and f3 of x function of t only. This assumption has effectively separated the three independent variables in the original function f, capital F, into the product of three separate functions. Each contains one of three variables. The three separate function f1, f2, f3 will satisfy three individual ordinary differential equations. Okay, f1, f2, f3 separate ordinary differential individual satisfy ordinary differential equation. This is a remarkable point, and involving separation constants. Okay, involving separation constants will be demonstrated in an example presented here in section 7.6. The solution of f1, f2 and f3 from these ordinary differential equations will result in the original function f, which is the solution to the original partial differential equations, and essence of separation of variables, a PDF partial differential PDE with two variables, two ODEs, each involves one of the two variables, a PDF with three variables, three ODEs, each involves one, there is a PDE. Okay. Partial differential equation or transverse vibration of strings. Okay, here is the strings and the other vibrations. Transverse vibration of a string or long flexible can structures in reality is used in common structures such as power transmissions, lines, guy wires, suspensions, bridges. These structures, flexible in nature, are vulnerable resonant vibrations which may be devastating to our society due to overall structural failure. Radio tower supported by guy wires. This is the radio tower and this supported guy wires. Okay, partial differential equation in the transparent variable strings. For these are the most usage in the PDEs. Long power transmission lines. This is the long power transmission line. Here the long power transmission line. Here the also long power AC power transmission lines. Here is the usage of PDEs. And a cable suspension bridge at the verge of collapsing. This bridge, a verge collapsing lines collecting some. Here is the line, and this also be used for PDEs. Here is the usage of PDEs, most effectively usage. Okay. And vibration analysis of a string or long cable structures. It is an important subject for mechanical and structural engineers in their safe design of this type of structures. Mathematical modeling of vibrating flexible structures with the derivation of appropriate differential equation may begin with the illustration of the physical situations in figure. Here is the figure are the vibration analysis or strings or long cable structures. Here you are understanding time to understand these structures. This is very simple, is the delta x, change in here, and x, here is the x and change in the x, and 0 or from origin 0, and here is the y, here the axis is L at time t is equal to 0, c detail A, here is the point, amplitude of vibration u of x comma t function at t greater than 0 equilibrium position, t is equal to 0, mass center here, and this is the change between x, here is the change, and p alpha, here is the curve. Okay, u x plus change in x. Okay, figure vibrating a string. Here is u and u is change, p and p is change, and change in alpha and alpha. Okay, this is a very simple figure, also important in engineering. Okay, assumption and derivation of partial differential equation for lateral vibration of strings. Like all engineers analysis, there are a number of assumptions. These assumptions are the string inflexible. This assumption means that the string has no bending strength, hence it cannot resist bending moment, and there is no shear force associated with its deflection. There exists a tension in the string. Why it is designated as P, which is so large that the weight but not the mass of the string is neglected. Every small segment of the string along its length, the segment with length delta x, moves in the vertical direction only during vibration. The slope of the deflection curve alpha is small. Okay, the mass of the string along the length is constant. The string is made of same material along the length. This is a remarkable point. String is made of same material along the length. Let the mass per unit length of the string be m, the total mass of the string, and incremental length. It means that incremental length means the change in length, changeable length in x. Delta x means change in x. Will this be m change in x delta x? The condition for a dynamic equilibrium according to Newton's second law or equation of motion can be expressed. The relationship for all small segment of the cable, the following dynamic force is generated associated with the vibratory moment up and down from its original equilibrium position. Applied force summation F is equal to mass of cable segment m multiplied by acceleration A, from which we derive the partial differential equation PDE to model the lateral vibration of an initially sagged string subject to an initial disturbance in the vertical direction. This situation is similar to a mass vibrated from its initial deflected position by small instantaneous. The initial shape of the string is described by function f of x in the figure to the left. Here the function described f of x, and x is equal to 0 point. Here the string. Okay, here the limit L and x, shape instantaneous displacement at x at time t, u of x comma t is function. Okay, so the partial differential equation for a lateral vibration of a string, the length of the string is equal to L and it's fixed at both sides, both ends, and x is equal to 0 and x is equal to L. Here the x is equal to 0 and x is equal to L. Here is the limiting part. Vibration after t is equal to plus 0, and here is the instantaneous displacement here from here, and this is the string here, and this is the shadow. Okay, the deflection of the string at x distance from the end at x is equal to 0 at time t into the vibration can be obtained by solving the following partial differential equation. This is the partial differential equation in which alpha is equal to radical p upon m, which p is tension in the string and m is mass density of the string per unit length. This is a very simple topic for mathematical students and engineering students. The PDE and the specific condition, the deflection of the string at x distance from the end at x is equal to 0 at time t into the vibration can be obtained by solving the following partial differential equation. Here the partial differential equation. The specific conditions are initial conditions, condition of the string. Okay, condition of the string. Initial condition, condition of the string before vibration takes place. U of x comma 0 is equal to f of x function. Here is the function describing the initial shape of the string before vibration, and here is the partial u of x comma t with respect to t, partial t, and initial condition t is equal to 0. 0 is the initial velocity of the string before vibration. The string's initial velocity before vibration, and the mathematically described this form. Boundary condition, the end condition of all times u of 0 comma t is equal to 0 and u of l comma t is equal to 0. And solution of a partial differential equation by separation of variable method. We realized a fact that there are two independent variables x and t involved in the function u of x comma t. We need to separate these two variables from the function u of x comma t by letting u of x comma t is equal to x of t, t of t, in which the function f of x involves the variable x only, and the other function t of t involves the variable t only. The relation in equation leads to here and here. Likewise, we may express the second order partial derivatives as here and here. By substituting equation 3 into the equation 1, we get here. After rearranging in the terms, we have left hand side here from here. We realized that the fact left hand side function of the variable only, this is the left hand side function, and the right hand side function of the variable x only, here the right hand side function variable x only. The only possible way to have left hand side is equal to right hand side is 1 over a square t of t d square t of t over dt square is equal to 1 over x of x d square x of x over dx square is equal to negative beta square. This is alpha, in which beta separation constant. Note that beta is a separation constant, positive or negative, the value of which needs to be determined. I have also written in this page. We will thus get two ordinary differential equation from 6. Okay, previous time we learned that 6 equation and 2 ordinary differential equation, here 1 and 2, here the equation. After applying some separation of variables as illustrated in equation 4 previous page, the specified condition in equation 2 also in previous page, we get two sets of ordinary differential equation with a specific condition as here, and this is the initial condition. Okay, t is equal to 0 is equal to 0, and both equations here second order differential equation, we have learned how to solve them. T of t is equal to a sin beta at plus b cos beta at, and x of x is equal to c sin beta x plus d cos beta x. Because we have assumed that u of x comma t is equal to t of t, x of x as in equation 4, upon substituting the solution of t of t and x of x in equation 9a and 9b, we have t of t is equal to a sin beta at plus b cos beta at, x of x is equal to c sin beta x plus d cos beta x, u of x comma t is equal to a sin beta at plus b cos beta at and multiplied by c sin beta x plus d cos beta x. This is the equation become 10, where a, b, c and d are arbitrary constant need to be determined from initial and boundary condition given in equation 7ab and 8ab. Determination of arbitrary constant. Let us start with the solution. X of x is equal to c sin of x sin beta x plus d cos beta x in equation 9b. From equation 8a, x of 0 is equal to 0 imply c sin beta steric 0 plus d cos beta steric 0 is equal to 0, which means that d is equal to 0, x of x is equal to c sin beta x. Now from equation 8b, x of l is equal to 0 imply x of l is equal to 0 is equal to c sin beta l. At this point we have the choices of letting c is equal to 0, sin beta l is equal to 0 from the above relationship. A careful look at these choices will conclude that c is not equal to 0, y, which leads to sin beta l is equal to 0. The above expression is effectively a transcendental equation with infinite number of valid solutions with beta l is equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi up to nth pi, in which n is an integer number. We may thus obtain the values of the separation of constant beta to be beta n is equal to n pi over l, where n is equal to 0, 1 up to nth numbers. Now if we substitute the solution of x of x in equation 9b with d is equal to 0 and beta n is equal to n pi over l with n is equal to 1, 2, 3 up to n into the solution of u of x comma t in equation 10 below, u of x comma t is equal to a sin beta t plus b cos beta at, c sin beta x plus d cos bx, we get u of x comma t in this form. Here is n is equal to up to n. By combining constant a, b and c in above expression, we have the entrant solution of u of x comma t to be u of x comma t is equal to a, and into this form. We are now ready to use the two initial conditions in equation 2a and 2b, determine constant a n and b n in the above expression. Let us first look at the condition equation 2b here and here. But since sin n pi over L x is not equal to 0, y imply n is equal to 0 imply here the only remaining constant to be determined are Bn in equation number 13. Okay, determination of constant coefficient Bn in equation number 13. U of x comma t is equal to summation n is equal to from 1 to infinity Bn cos n pi over L multiplied by t sin n pi a over L x. The last remaining conditions of u of x comma 0 is equal to f of x will be used for this purpose, in which f of x is the initial shape of the string. Thus, by letting u of x comma 0 is equal to f of x, we will have u of x comma 0 is equal to in this form, where limits 0 less than or equal to 0 involved, L involved, and also x also involved. There are a number of ways to determine the coefficient b and in equation 14. What we will do is to borrow the expression that we arrived from Fourier series in the form, okay, then f of x is equal to summation n is equal to 0 to infinity bn sin n pi x. The coefficients bn of the above Fourier series in this form, bn is equal to 2 over L integral condition 0 to L f of x sin n pi x over L dx. The complete solution of the amplitude of vibrating string u of x comma t becomes in this form, okay. Modes of vibration of a string. Here are the modes of vibration of a string. Here the string, here the x is equal to 0 point, here the limit L vibration after t is equal to 0 plus, and here the instantaneous displacement shape at t is equal to f of x initial shape. Here the shape of a string, here f of x function here, and this is the instantaneous. We have just derived the solution of the amplitude of a vibrating string u of x comma t to be here. We realized from the above from the solution consists of infinite number of terms with n is equal to 1 and n is equal to 2 and n is equal to 3 up to nth. What it means is that each term alone is a valid solution. Hence u of x comma t with one term with n is equal to 1 and is one possible solution, and u of x comma t's function with n is equal to 2 only is another possible solution, and so on and so forth. Consequently, because the solution u of x comma t also represent the instantaneous shape of the vibrating string, there could be many possible instantaneous shape of the vibrating string. Depending on that, the term in equation 16 is used. Predicting the possible form of instantaneous shapes of vibrating string is called modal analysis, okay. And first three modes of vibrating system. The mode 1 is n is equal to 1 in equation 16, previous page, and here is the form. The shape of the mode 1 string can be illustrated according to equation 17 is here are the string, here are the shape, here are the limits. We observe that the maximum amplitudes of vibration occur at the mid span of the string. The corresponding frequency of the vibration is obtained from the coefficients, the argument of the cosine function with time t here, where t is equal to tension in Newton or pounds and m is equal to mass density or string unit length, okay. This is your last page. Mode 2 with n is equal to 0 in equation 16, u2 of x comma t is equal to b2 cos 2 pi a over L t sin 2 pi over L x. Here is the string, here is the shape, here is the limits. Maximum amplitudes occur at two positions with 0 amplitudes at t at two ends, and mid span frequency f2 is equal to 2 pi a over L divides L over 2 pi is equal to a over L is equal to 1 over L here. Mode 3 with n is equal to 3 in equation 16 u of x comma t is equal to b3 cos 3 pi over L t sin 3 pi over L. Here the strings. Model analysis provides engineer with critical information on where the possible maximum amplitudes may exist when the string varies, and the corresponding frequency of occurrence. Identification of locations of maximum amplitudes allow engineers to predict possible locations of structural failure and thus the valuable location of string long cable structures. I hope that you understand my topic, and so thanks for watching my video, and please subscribe my YouTube channel, like, comment